revisiting one of the problems that we did last time to kind of motivate the new topic worth of stuff. And because we'll do it in a different way that's still implicit, but let's see. Still implicit, but maybe we can see how we might use this trick in other situations. Okay, so let me start with the equation xy equals 1. Okay, and what was the goal in all this? To find dy dx. Yeah? Huh? Yeah? Okay, so we did this two different ways last time, right? The first way was we just solved for y and then did it with the power rule. Okay. The second way was that we just said, all right, let's treat this implicit, take the derivative of both sides, and then solve for dy dx. Okay. And in that solution, when I did the derivative of both sides, what did I have to do on the left? Yeah, I had to use the product rule. Okay. And so that said it was x times dy dx plus y times 1. Okay, right? First times root of second plus second times root of first. Okay, good. Yeah. Okay. And then we needed to solve for dy dx. So the first thing we did was move the y over and then divide by x. Okay. And then if we wanted to, we could have replaced y with 1 over x, but we didn't necessarily have to. And there were some of the other examples that we looked at last time where, well, we couldn't solve for y, so we just had to kind of leave it like this in terms of both x and y. Okay, good. So let's look at a different way that we could have approached this that still is implicit, but could have avoided the product rule. Okay. Now you might look at that, the equation, and say, wait a minute, Dr. McKinney, how can I avoid the product rule when there's very obviously a product right there? Okay, if we did that, we'd be doing it explicitly, right? Because, yeah, you're right. If I solve for y in terms of x, then I don't need the product rule because I can just do it with the power rule. Okay, so let's think of another way to do that. Okay, and my hint here is how can we take a product and turn it into something else? How can we turn a product into a sum? I mean, I can't just write a plus sign in the middle, right, for for no good reason. What turns products into sums? The logarithm. Okay, so is this valid? Can I just take the log of both sides? Okay, fine. What's the log of 1 on the right-hand side? Yeah, log of 1 is 0. What about the log of xy? How could I rewrite that? No, not quite. There you go. Natural log of x plus natural log of y. Right? That's the whole reason that Napier came up with the logarithm in the first place, is because it can take a product and turn it into a sum. Okay? Okay, so how does that help us? I wanted to take the derivative of this thing, right? So let's take the derivative of both sides of this equation. Okay, so just take the derivative of each piece. Now, what's the right-hand side? 0, right? It's constant, no big deal. What's the derivative of natural log of x? 1 over x. What's the derivative of natural log of y? 1 over y times the derivative of y, which is dy dx. Okay, So what was the derivative of log of some stuff? 1 over the stuff times the derivative of the stuff. Okay, so why did we have to multiply by the derivative of the stuff? Because of the chain rule. Now, why did I not have to do it with the 1 over x term? Because what's the derivative of x? And multiplying by 1 doesn't really change anything, does it? Yeah? Okay, now, can I solve this equation for dy dx? Yes. Oops, sorry. Do it in 2 steps. And we get exactly what we got the other way. Okay, so what was the idea here? Right, what was the key idea to this approach? Yeah, avoiding the product rule, or maybe put another way, it's the fact that a product or a quotient, those are kind of messy to deal with when you're taking derivatives. What's easier to deal with when you're taking derivatives? Sums and differences, right? Because the sum, you just take the derivative of each piece and then put them together at the end. Same thing with the difference. We? Okay. And what can turn products into sums and quotients into differences? The logarithm can do that. And it's, like I said, why Napier came up with it in the first place. Okay, so let me make kind of an analogy here. It's not the best analogy in the world, but let's see. A couple of you guys have on hoodie t-shirts or hoodie sweatshirts, okay? Now, we'll go with Arthur's because his isn't a dark color. But what would happen if you got like some grass stains or ketchup stains on that hoodie? Huh? Well, okay, yeah, it might not come out, but how would you wash it to try? Okay. Now, how many of you would just shove it in the washer? I mean, you're college students, right? So that's the washing machine's job is to, right? Okay, but Arthur would pre-treat it, maybe. That's probably wise. Okay. Now, let's assume that we had 2 identical hoodies with 2 identical ketchup stains. And one of them we just throw in the washer, and the other one we do the pre-treating on. Which one's probably going to come out a little better? Probably the pre-treated one. Okay. So think of the logarithm here as pre-treating the laundry. Okay. By doing a little extra work at the beginning with the logarithm, we can actually save ourselves some trouble later by not having to deal with necessarily as much product rule type stuff. Okay. Um, yeah. Okay. So does that kind of make sense? Um, all right. So where this can pay real dividends is, um, let's say, for example, um, what's the derivative? Oops. What's the derivative of e to the x? Okay, fine. What's the derivative of a to the x, where a is a quantity larger than 1? No. Okay, so that would be true if x was a number and a was the variable, right? So you just gave me the derivative of x to the a. Okay, do you guys see the distinction between these? Yeah, it's which one is the base? Is the base a number or is the base the variable? Okay, and um, oh, we don't have a new sheet just yet. Yeah, and that's actually the one from Calc 2 yesterday, so you definitely don't want it. um, okay, so this is different than this. Okay, and you can't use the power rule on this one, but you can on that one. Okay, so you guys see the distinction between what each one is in form? Yeah, okay. So what was the derivative of a to the x? Well, if a is e, what do we get? Yeah, we just get the same thing, but there's this annoying natural log of a that we have to kick out. So what I'd like to demonstrate is why that natural log of a is there. Okay, we could just take it on faith and memorize it. Okay, but let's actually demonstrate why it has to be there. Okay, so does that make sense? All right, so to do that, what I'm going to do is start by writing y equals a to the x. Okay, that's the thing we want to take the derivative of. Yeah? Okay. What's the annoying thing here? We've got an exponent, right? Wouldn't this be a lot easier if we didn't have an exponent? So what would happen if I hit log of both sides here? How can I simplify the thing on the right? Yeah. Okay. So the logarithm kind of have actually three magical powers. It turns products into sums, quotients into differences, and exponentiation into multiplication. We'd have to do another log, okay? But I think as you guys will see, it's not worth like throwing an extra set of pre-treating on already the pre-treated ketchup is not really going to help much more, right? There's sort of a limit to the well, both the analogy and the technique. Okay, so we remember that logarithm property. Okay, now you guys are starting to see why the assessments had all this stuff with logs on them because of today. Okay, so now I want to take the derivative of both sides of this equation. What's the derivative of the left? 1 over y dy dx. Okay, what about on the right? You fool, you fell for one of the classic blunders. What is a? Hmm? It's a number. It's a number bigger than 1 by assumption. So what's the natural log of a? Some sort of number, right? Do I know exactly which number it is? No, but it's just a number. So what's the derivative of 2x? What's the derivative of 5x? What's the derivative of x times some random number? That random number. So what's the derivative of x times the natural log of a? Just the natural log of a. That's the number. Okay, you guys, so what I'm trying to say is this structurally is no different than the derivative of x times 3. And what's that derivative? Just 3, the number. Okay, yeah. Yeah, you can. Okay, so, and I see your point there. If you do, I write it like this. Okay, and the reason is that the x is not inside the logarithm. Okay, and by using the parentheses, it makes that clear so that you don't think mistakenly that it's this, right? Because it's not the same thing. Okay, so is that okay? Right? Okay, but once I write it like this, do we see how this is the same as like if I had 2 times x? Yeah? Okay, now you look at that and you say, well, wait a minute, but a is a, I don't know what a is, but what kind of object is it? It's just a number. We just don't know its value. Okay? All right, so just to recap then, what's the derivative of a number times x? Just that number. Okay, and so we got that. We Okay, now what's the goal in all of this? To solve for dy dx. So I can do that by just multiplying both sides by y. And then I say, well, wait a minute, what was y? It was this, back from the very beginning, right? So can I substitute that in? And I get exactly what we had memorized that this derivative should be. Okay, so this is sort of a good thing, because what would happen if you were dealing with a problem and you came to this and you're like, oh crap, what is it? Is it divided by natural log? Is it times natural log? I don't remember. Well, are you hosed? No, because if you got a few minutes, you could go through this derivation to figure it out. Okay, so that's maybe proof of it. Okay, we no. All right, so let's look at a really, really easy, I mean, evil, sorry, not easy, evil problem next. Okay, so, but let me pause for any question, preguntas, and or fragens. Good? Okay, so let me write down two basic rules that we've already seen. Okay, um, the one on the left is exponentiation, okay, the one which is what we just derived. The one on the right is the power rule, okay? And like we were talking about a minute ago, what's the difference between, how do you know which situation to use? The one on the left, what's the base? It's a number. What's the exponent? The variable, okay? Or something in terms of the variable. Whereas for the power rule, what is it? The base is the variable, and the exponent is a number. Okay, so you see how they're kind of flippy-flopped, and accordingly have two different basic rules? Yeah? Okay. All right, so I'm going to be really, really, really evil. And suppose that these two things got together and had a baby. Okay. And I want to know what the derivative of x to the x is. That's a weird function. Okay. Do either of the previous rules apply? I'm getting a very timid head shake over here and a very timid sure over there. And everybody else is looking puzzled, wishing that it was spring break all freaking ready. Um, yes, I have psychic powers. No, it's like I've been teaching for like 12 years or something. Yeah. You think yes, with gusto. Absolutely not. No. Okay. We cannot use either of the rules from above. Okay. So the answer is an emphatic no. Okay. Why can't we? Well, okay. Yes. That'd be too easy if we could just. True. It is not rocket science. Hmm? And we don't have that here, right? Because in this situation, what's the base? It's a variable. What's the exponent? Also a variable. Our two previous cases don't cover this, right? Because both of them had either the base or the exponent being a number, right? And I don't see a number here. Okay, so are we hosed? Hmm? Are we completely hosed? Oh no, of course not. What can we do? D&E does not exist? No, the answer most certainly exists. Yeah, okay. You can't just like be an ostrich and bury your head in the stand and pretend that the problem doesn't exist. And, because you know what's going to happen? It'll keep appearing on assessments until you get it. Well, what have we been doing all day? We've been throwing logarithms around, right? So let's write this and apply a little bit of stain pretreater. So take log of both sides. You missed that part, Patrick. You pretreater. Yeah, you missed the analogy. Okay, so if Arthur there gets a ketchup stain on his hoodie, how are you going to get it out? Now, most college students are probably just going to throw the thing in the washer. That's the washer's job. Right. Okay. But what about if you apply a little bit of stain pretreater to it? Is it going to come out a little better? Okay. If your mom did it. Yeah, exactly. Okay. Yeah. She probably uses like Breeze or Gain Flings or whatever. Yeah. Okay. So, yeah. So let's hit both sides with the logarithm and pre-treat the stain before we get at it. Yes. Okay. So we're there. And I haven't done any calculus yet. I've just changed algebraically the way the equation looks. Okay? All right. So what was the whole goal here? It was to take the derivative of both sides of this. Okay? So I'll just hit both sides with my ddx operator. Okay? And on the left, what's the derivative of natural log of y? 1 over y times dy dx because of the chain rule. Okay, so that part is the um, same as before, right? Ah, okay, good. Um, so what do we have to do on the right-hand side here? Right, but how do we do that? We want to take the derivative of x natural log x. How do we have to do that? We have to use the product rule because x is a function, a natural log of x is a function, and they're being multiplied, yes? Okay, so what's the derivative of a product? First thing times the derivative of the second plus the second thing times the derivative of the first. Okay, product rule. We? Uno. Okay. So I've written the instruction to take the derivatives just to make sure that we had the product rule step correct. Now let's actually break up each piece. So what's the derivative of natural log of x? 1 over x. What's the derivative of x? Just 1, so I don't have to write anything. Okay, so do we buy this step? Take a moment to absorb and meditate deeply upon it. We? Okay, so can I simplify this a little bit? Yeah, because what's x times 1 over x? 1, that's nice. And then the other thing I need to do is just multiply both sides by y. Okay, and then one further step, but we'll do that in just a second. So what was y? X to the x. That's what we started with at the very beginning, right? So I get here 1 plus natural log of x times x to the x. Now, I think you guys will agree that we probably didn't expect it to be to come out like this from the get-go, but that's what we got. Okay, Gucci. Yeah. All right. So let me give you guys a couple of problems to work out. Okay. And so we'll just do number 1, number 2, number 3, and number 4 for the different ranks of the classroom. Number 1 gets y equals x to the e to the x. Number 2 gets y equals 3x squared plus 5 to the 1 over x. 3 gets y equals natural log of x, whole thing to the x. And 4 gets secant of x to the 3x. Okay, good? All right, so let's take a minute and give these a shot and confer with your compatriots at the table. And I'm going to mute the stream here and walk around.